Sherpa for Underground Mines is a Windows-based application. It's designed to enable clients to estimate the capital and operating costs associated with proposed underground development scenarios. These costs are estimated to a pre-feasibility level. The program uses an engineering-based approach in that it doesn't rely on parametric or statistical algorithms to arrive at the results. In other words, it uses the same types of calculations that an engineer would use if they were doing a spreadsheet-based approach to estimating costs. Clients can work in either English or metric units. The program presents as 4 separate menus in Echelon. Titles for each data entry screen are listed on these menus. The first menu collects data about the project and the mine design. The second suggests equipment combinations for the users, and users can overwrite and adjust each machine suggested by the program. The third menu displays engineering calculation results and allows users to override those results with their own data if they have it. And the fourth menu displays all the result screens. Each screen contains a series of cells where users can enter data about their project. Data can either be typed in the form of values, or some cells require text entries, which are generally displayed, the options of which are displayed in list boxes on the screen. The program allows users to estimate costs with very little initial information. It also, of course, allows people with much more information to tailor the cost more directly to their project. Obviously, the more information about the project that a client has, the more reliable the results. Projects can be broken down in a series of production segments. That'll be displayed here in a minute. Help screens are available for each entry cell. These screens allow users to understand the calculations that might come into play when estimating the values displayed in the entry cell. They might have suggested values for those entries, or they may just be suggestions as to what the user might enter. Each screen can be printed directly. Transferring from one screen to the next is done by clicking on arrows at the bottom of the screen. These arrows are also available on each menu. Every time you click an arrow, the program performs a series of calculations. The best way to demonstrate program use is to go through an example here. So let's take a look at a mine that has about 8,200,000 tons of resource. We'll operate 10 hours a day, 10 hours a shift, 2 shifts a day, 320 days a year. We'll start out at 800 tons per day. And we'll say that our mine can be accessed, at least initially, from an adit. And ore will be hauled to the surface using a rear dump truck. And we'll say that this segment of the project runs from year 3 to year 5. There are currently 8 different stoping methods available in the program. As will be demonstrated here in a bit, there are dozens of variations to these methods, and the program is set up to allow users to adjust all the development necessary for each type of stoping method in a way that really allows them to design their method as they see fit to fit their scenario. In each production segment, you can use 2 different stoping methods. In this case, let's say we'll have cut and fill. We'll slush the material to an ore pass. We'll collect it at the bottom of that pass using a rear dump truck. And let's say 80% of our production comes from that type of stope. We use shrinkage stoping for the rest. And we'll collect material using scoop trams, and we'll also transport to a transfer point using those scoop trams. in the second production segment. Again, we'll operate 10 shifts or 10 hours per shift, 2 shifts per day, 320 days a year. But let's double our production, and we'll do that by adding an adit, which I'll show in a minute. We'll say that goes from year 6 to 13. Again, we'll use cut and fill. We'll slush to a ore pass, collect with the rear dump truck, but only 60% of our ore will be produced using cut and fill. The remaining 40% will be recovered from shrinkage stopes, and the muck will be collected using scoop trams and hauled using the same machine. Now in the final production segment, let's assume we've gone deeper into our deposit. Again, 10 hours a shift, 2 shifts a day, 320 days a year. Let's put our production rate at 1,200 tons per day, and let's say from this point forward we hoist our material. And we'll do that through the rest of the life of the project. We'll again use cut and fill, stoping. We'll slush to the ore pass, we'll collect with rear dump trucks, and those trucks will haul it to the hoist station. But let's say 100% of our production is now from cut and fill stopes. The deposit we're mining, let's say it's a vein deposit. Notice the program will let you design around 4 different types of deposits, but you can vary these dimensions to emulate almost any scenario. Say it dips 70 degrees, the length is about 4,000 feet, it's 12 feet wide, 2,000 feet high on average, and from the top of the deposit to the surface is maybe 800 feet, but there is a horizontal access point 4,500 feet away. We said that in the second production segment we're going to add an adit. The program automatically adds the first adit, but if we want to give another one, we have to add that ourselves. We'll make this similar to the first one. We'll put it in the footwall. 14 feet wide, about 12 feet high, same length as the first adit, same gradient. We'll drive this adit in years 4 through 5. And we'll shotcrete the whole thing. And this will be our second adit, and if you note, it's just similar to our first adit. So we have 2 adits accessing the deposit. First, the first one is available for haulage in year 3, and the next one is available for haulage in year 6. We specified hoisting starting in year 13, so the program automatically adds a shaft in that year. Now with just this information that we've entered, the program can take that data, do all the calculations necessary, and use suggested values for things that are not readily apparent. The program suggests these values to come up with a cost estimate. In this case, our pre-production development costs and equipment purchase costs occur in years 1 and 2. Production starts in year 3. In year 4 and 5, we're driving that second adit, so those costs are a little higher. In year 6, we double production, so we purchase more equipment. Our operating costs go down for this period of time. In year 13, we want to complete our shaft and start hoisting in year 14. So the shaft development costs are reflected in the operating costs in years 12 and 13. Some development hoisting equipment is purchased here, but our major hoisting equipment is purchased in year 14. And from year 14 on, costs reflect a scenario where we're hoisting the ore to the surface. All the calculations, all the data entry, everything about the program is fully integrated. By that, I mean if you change something, the program follows the changes all the way through, recalculates everything from that point forward, and then reflects the impact of your change on everything from the size of the worker change house to ventilation requirements to equipment maintenance requirements, everything. And that's a key aspect of the program. Just as an example, let's look at our ventilation requirements. The fan horsepower size is 371 horsepower, and that'll be during our second production segment is where the maximum horsepower is required. Horsepower ventilation requirements in general are based on the equipment, if it's diesel equipment, exhaust dilution requirements, and the worker requirements. But let's say we need 371 horsepower given the scenario we've designed. If we were to go back to these two adits and change the dimensions, make them 8-foot by 10-foot adits, that change in design carries through all the calculations of the program, and we'll see that we now need a much bigger fan because of the increased resistance of those two adits, of the airflow through those two adits. So one of the key points of the program, as mentioned, is that changes in design carry through, and everything impacted by those changes, the costs associated with those are reflected in the results. Change our dimensions back to the original dimensions here, and we'll go through some of the screens. Briefly, as I mentioned earlier, any stope configuration more or less can be altered by altering all the development work required to access and develop those stopes. For instance, all the drift and crosscut needs for this mine are calculated by the program and listed as how many feet are required prior to production in the daily advance, how much of it is going to be in ore, how much of it is going to be in waste. Same for crosscuts, prior to production, daily advance, where these crosscuts are. In the manual, there are plates, designs for each type of stoping method that the user can refer to know how the program bases its estimates, and then you can of course alter those to reflect your own conditions. So drifts and crosscuts can be altered. Draw points and access raises, same thing. You can change the face areas, the number per stope, the length, the amount in each constituent or footwall, hanging wall, how much prior to production and how much during production. So you can alter draw points and access raises in that way, as well as ore passes and ventilation raises. Let's go back up here real quick and look at ore and waste characteristics. You can alter these, and of course should alter these, to reflect conditions at your own deposit. These are used in a variety of ways, of course, but powder factors are calculated with these numbers, drill patterns, bucket and bed sizes, conveyor sizes, hoist capacities are all based on this type of material. So these numbers need to be well thought out, although the program will suggest numbers for you. Although, as said, there are help screens available for each, which allow you to have data at your fingertips to substitute for what the program suggests if you want. Cost information such as supply prices, wages, salaries, and we'll see in a minute equipment purchase prices, are for the most part from Mining Cost Service. And that's publication of InfoMine USA. In the equipment selection, we'll briefly look at a couple of these screens. For the development hall, you can see the options available from hauling. This is for development, so while we're driving drifts, crosscuts, adits, these are the machines used, available, and these are the ones used in the program. So you can alter the type of machine, the size of the machine. You can alter the haul distances and the haul gradients, all to reflect your design. Look at skips and hoist for a minute. We do have a hoist in there. These are the typical hoisting calculations or parameters used in the typical hoisting calculations you'll find in most engineering handbooks. Again, you can alter all this information. The program or values suggested by the program are based on the data we entered earlier, but you can alter any of this information to reflect conditions for your own design. In the engineering calculations, here's where you can alter some of the results of the calculations done by the program. For instance, we have cycle times to the surface, hourly use for the machines. Now these are for the trucks up here. And for the hoist down here, we only hoist in years 14 through 22. Notice that we have a 1,200 ton per day production rate, but of course that is just the ore. There's also waste development associated with it. The program calculates that waste development for you and adds it in. Here's our hourly use for the hoist each day and the average horsepower draw. We looked at this screen a little bit earlier. This is the ventilation horsepower calculations. The requirements for both the workers and to dilute the diesel fumes for the equipment. The intake opening parameters, the exhaust opening parameters can all be changed. These are of course used in the horsepower calculations. And we come up with the horsepower. The program of course buys the biggest horsepower fan you need over the entire course of the operation. Equipment purchase prices are listed here and are listed so that you can change them. If the user has better information, they should overwrite, of course, what the program suggests. Here's the equipment used in the primary stopes, the secondary stopes, the operation itself, the trucks. That's during the first production segment. Over here we'll have the hoist. You can alter that price during the third production segment. And the cost of the development equipment. The equipment used to drive the drifts, crosscuts, raises, etc. Program estimates a workforce for you. As well as a salaried staff. And then we're on to the results. Again, just to emphasize the point, all the suggested engineering parameters, the equipment suggestions, the calculations done by the program can be overridden by the user with their own information if they have better information. And we encourage that, of course. The more design data that the user inputs, the more representative the costs. And that's, of course, the goal. So supply operating costs, all the operating costs, in fact, are listed in terms of either dollars per ton, dollars per day, or dollars per year. And each is summarized on a separate screen. The program also estimates daily use of diesel and the daily power draw. Also can list those in terms of diesel use per ton ore and power draw per ton ore. The program works on an annual basis, so this is in production year 3. You'll see as we go along, this value changes depending on what production segment we're in. Hourly labor is displayed in a similar manner as is salaried labor. Equipment operating costs are broken out for the primary stopes, the secondary stopes, development and production, and are calculated for each year of the project. These are also displayed in either dollars per day, dollars per ton, or dollars per year. Equipment requirements are also broken out in a similar manner. The number of machines, the price of each for each production segment. So we have the hoist here in production segment 3, and back to the trucks here in production segments 2 and 1. The overall equipment capital costs are listed separately as well. Development capital costs are listed for all the openings, the shaft, the 2 adits, the drifts, crosscuts, draw points, access raises or passes and vent raises. Adit 1 is driven in years 1 and 2, Adit 2 in years 4 and 5, and the shaft is over here in years 12 and 13. These can also be displayed in terms of dollars per foot or dollars per meter. Surface facilities costs include the costs associated with a mine office, a worker change house, a mine warehouse, a surface shop, and a mine plant building. The program estimates the facility size for each and the unit cost per square foot of each. We've looked at the project cost summary already. The program also separates out shaft and adit construction costs. The program assumes that the work is done in-house, so no contractor markups are added. But here we have the labor costs, the equipment operating costs, and the supply costs for the shaft, both in terms of total dollars and dollars per foot. And the same for the adits. Each project course can be saved to a file. It can be printed both directly to a report. Different reports are available here, and these can be printed directly to a printer. Or they can be printed to a file. And this file can be then imported directly into an Excel spreadsheet. They're common delimited text files. And that's about it.